In chemistry, when we make measurements, we use the International System of Units. The International System of Units is the most modern version of the metric system. So it's important to recognize that all measurements require 3 parts at least. They have a number that tells you how big the thing is that you're measuring, an error that describes the uncertainty in the measurement, and units that tell you what is being measured. So if we break down this measurement here, we can see from the units that what is being measured is temperature. We can see from the plus or minus 0.2 the uncertainty, and when we put that all together, what we can tell is that the temperature is somewhere between 27.3 degrees Celsius and 27.7 degrees Celsius. So what we're focusing on in this section are units, and what the units are a label that tells us what is being measured. For example, when we see the familiar unit gallons, we know that volume is being measured. If we see the unit miles, we know that length is being measured. So if we look at a drug fact label, like this one for this antihistamine, we see a whole bunch of numbers, and then there is always a unit afterwards. This first one here is milligrams, which tells us it's a unit of mass. This one here is years, which tells us it's a unit of time. Similarly here we have hours, which is another unit of time. And at the bottom here we have degrees Celsius and we have degrees Fahrenheit, which tells us that they are talking about temperature. As I mentioned in the introduction, in science we use the International System of Units. This was developed in France, and the French name is Le Système International des Units. For this reason, people will often refer to the International System of Units as being SI units. This is the initials of the French name. What this system is the most modern version of the metric system. So scientists and health scientists prefer the metric system over the English system because the relationship between different units are always powers of 10. So 1 centimeter is equal to 10 to the minus 2 meters. 1 milliliter is equal to 10 to the minus 3 liters. So you can see the difference between these units in each case is simply a power of 10. So it's quite easy to do math with powers of 10, and it's also easy to remember powers of 10. In contrast, in the English system, the factors that convert between different units are not normally powers of 10. You're probably familiar with the fact that there are 12 inches in 1 foot and 4 quarts in 1 gallon. Now, if I was to ask you how many teaspoons are there in a quart, you'd probably be very confused. And the reason is because it's difficult to remember conversions that are not based on powers of 10. So there are 7 base units in the SI system of units. Each unit has a name and an abbreviation. So the base unit of length is the meter, which has the abbreviation lowercase m. The base unit of mass is the kilogram, which has the base unit kg. The base unit of time is the second, which has the abbreviation S. The base unit of temperature is the Kelvin, which has unit abbreviation K. Now at this point it's worth noting that there is a difference in case here, isn't there? Most of the time the unit abbreviation is written with all lowercase letters, except for in the case where it's named after a person, and that only affects 2 of our units. So we do have to pay attention to that though. The case is important. The base unit for amount of substance is the mole, which has abbreviation MOL. The base unit for electric current is the ampere, and because it's named after Professor Ampere, it has abbreviation uppercase A. And the base unit for luminous intensity is the candela, which has abbreviation CD. Now, obviously there are many more than 7 things that we can measure, and when we want to get units for some of these other things, what we're going to do is we're going to combine these base units to form derived units. So for example, if I want to derive a unit for area, I'm going to multiply 2 lengths together, and so for that reason area has the derived units of meters squared. To calculate a speed, I'm going to take length and divide it by time. So the units for speed in the SI system are going to be meters divided by seconds. Now, powers of 10 are used extensively when working with SI units. Powers of 10 are useful because it's easy to remember the conversions between different units in the SI system, but they are also helpful because they allow us to express very large and very small quantities easily. To save us continuously writing out these powers of 10, a system of what we call metric system prefixes has been developed, where symbols replace multiplication by common powers of 10. So the metric prefix mega, which has the symbol uppercase M, means that our measurement is multiplied by 10 to the 6. The metric prefix kilo, which has the symbol lowercase k, means that our measurement is multiplied by 10 to the 3. The metric prefix deci, which has the symbol lowercase d, means that our measurement is multiplied by 10 to the minus 1. The metric prefix centi, which has the symbol lowercase c, means our measurement is multiplied by 10 to the minus 2. The metric prefix milli, which has the abbreviation lowercase m, means that our measurement is multiplied by 10 to the minus 3. And then the metric prefix micro, which has the Greek letter mu as its symbol, means that the number is multiplied by 10 to the minus 6. So instead of writing, say, 10 to the 3 grams, I can write 1 kilogram, and the K means the same as 10 to the 3. Instead of writing 10 to the minus 2 meters, I can write 1 centimeter, and the C substitutes for the power of 10. Again, instead of writing 10 to the minus 6 meters, I can write 1 micrometer, and the micro replaces the power of 10. These prefixes are super commonly used in health sciences, and you should remember these 6. Now, there are many more metric prefixes, and if you need others, you can always look them up in your textbook. So it's worth thinking about what are common objects that are relatable to the SI system of base units. So a kilogram is slightly more than 2 pounds. In fact, it's 2.2 pounds in 1 kilogram. And a quart of milk weighs about a kilogram. Now, in the chemistry lab, we're not going to be measuring out kilograms of stuff. We're probably going to be measuring out grams or milligrams. So one of the most common measurements that you're going to make in the lab this quarter is measuring the mass of something. And again, typically that's going to be grams or milligrams kind of amounts. Probably the next most common measurement that you guys are going to be making is a measurement of volume. Volume is the amount of space that an object occupies, and you might be familiar with some of the formulas that are used to calculate the volumes of sort of common objects. It's important to realize in all of these formulas, we're always going to be multiplying 3 lengths together. So what that means for us is that the units for volume are always going to be length cubed. So in SI units, you might see things like centimeters cubed, millimeters cubed. In traditional units, you might see things like inches cubed, feet cubed, or miles cubed. We're going to be measuring volumes almost every lab class. Now, the cubic meter is the base SI unit of volume, and that corresponds to the volume of a cube that has sides 1 meter. So that's a huge amount of substance, right? The cubic meter is a giant amount of stuff. 1 cubic meter of water weighs 1,000 kilograms. That's a lot, okay? So more commonly in the chemistry lab, we're going to be using volumes that are of the order of decimeters cubed or centimeter cubed. So it's worth thinking about how that sort of relates to a meter cubed. Now, chemists are kind of a little bit attached to the older metric units, and in particular we like to use the non-SI unit liter and milliliter to measure volume. And so a liter is the volume occupied by a cube with an edge length of 10 centimeters, which is the same as 1 decimeter. A milliliter is the volume occupied by a cube that is 1 centimeter on each edge. So that's important for us. What that means is that 1 milliliter is exactly the same as 1 centimeter cube. So if a liter is the volume of a cube occupied by that has the volume of a cube that has 10 centimeter edges, let's think about that in centimeters cubed. 10 centimeters cubed times 10 centimeters cubed times 10 centimeter cubed equals 1,000 centimeters cubed. So 1 liter is the same as 1,000 centimeters cubed. We also said that in every 10 centimeters there is 1 decimeter. So a liter is the volume of a cube that has 1 decimeter edges. So 1 decimeter times 1 decimeter times 1 decimeter gives me 1 decimeter cubed. So a liter is exactly the same thing as 1 decimeter cubed. So those 3 relationships are important. 1 milliliter is the same as 1 centimeter cubed. 1 liter is the same as 1,000 centimeters cubed, and 1 liter is the same thing as 1 decimeter cubed. There are a lot of equivalencies that you may need to use to relate metric or SI units to traditional units. And you can find these in tables online, and you can also find them in your textbook. If you do need to convert between traditional units and metric units, I will provide you with the appropriate equivalencies. Something that you guys will need to do is become proficient in using the 3 common systems of temperature. These 3 systems are degrees Celsius, Kelvin, and degrees Fahrenheit. And they're related to one another via these 3 formulas here. You do need to memorize these formulas. It's interesting to think about where they came from. The Fahrenheit scale was developed by Professor Fahrenheit, and he wanted a scale that had 2 qualities. He wanted the difference between the freezing point and the boiling point of water to be 180 degrees, because he considered boiling and freezing to be polar opposites, and as there was 180 degrees between the North and South Pole, he wanted 180 degrees between boiling and freezing of water. He also wanted to set body temperature to be, on average, 100 degrees Fahrenheit. Now, it turns out he got a little bit off there, but he's got pretty close. Professor Celsius thought this is madness, and what he did was he stuck a thermometer in ice water and he marked where the mercury rested as being 0, and then he stuck a thermometer in boiling water and he marked where the mercury came to rest as being 100, and then he divided that into 100 equal sections. So what we end up with are two scales where the difference between the 0 points is 32 degrees, and 1 Fahrenheit unit is smaller than 1 Celsius unit. In fact, a Fahrenheit unit is only 5/9 of a Celsius degree. So that's the origin of these formulas. The 32 accounts for the difference in the 0 points, and the 5/9 or 9/5 accounts for the difference in the size of the Fahrenheit and Celsius degree. Now, when Professor Kelvin came along and made his scale, he took a much simpler approach. The Kelvin scale works exactly the same way as the Celsius scale. It just has a different 0 point. The 0 point of the Kelvin scale is offset from the Celsius scale by 273.15 units. So this is important because we never will have negative Kelvin temperatures. Kelvin temperatures are always positive. And to convert between Kelvin and Celsius, all we have to do is add or subtract 273.15. The size of a Kelvin unit is exactly the same as the size of a Celsius unit. So whatever increase, say we increase by 2 Kelvin, that's exactly the same as an increase by 2 degrees Celsius, right? If the temperature of an object is increased by 5 degrees Celsius, there we go, then it's also going to increase by 5 Kelvin. So the only difference between these guys is the 0 point, and we just shift between one and the other by adding or subtracting 273. So measuring mass and measuring volume are very common measurements in the chemistry lab. Frequently, we will combine mass and volume to calculate the density. And we want to remember that density is equal to mass divided by volume. So later on in the lab, we're going to determine the density of some salt water. It normally comes out to be a little bit more than 1 gram per milliliter. So famously, seawater has a density that's pretty consistent at 1.03 grams per milliliter. What that means is every milliliter of seawater has a mass of 1.03 grams. What you guys want to remember for the next section is that whenever we are trying to convert between mass and volume, we're always going to be using density as our conversion factor. So that's an important little thing to lock away for future reference. So when we look at densities, we're going to notice a few things. Solids tend to be, in general, much more dense than liquids, and liquids, in general, tend to be much more dense than gases. So gases tend to be our least dense phase of matter, then liquids are the second least, and then solids tend to be the most dense phase of matter. Some important things to recall is that a centimeter cube is exactly the same as a milliliter, and that there are 1,000 milliliters in 1 liter. So if I see a density of 1.0 grams per centimeter cube, that's exactly the same as 1.0 grams per milliliter. Okay. Some other important properties of density are that an object will sink in a fluid it is more dense than. So when I look at this number 3 ball here, it's not sinking, so I know that it is not more dense than the liquid it is sitting in. Similarly, when I look at this oil here, it's not sinking, so I know that it isn't more dense than the water that is underneath it. So that leads to the second point. An object will float in a liquid that it is less dense than. So that tells me that the number 3 ball is less dense than the mercury that it is floating on. And in the second case, it tells me that the oil is less dense than the water. The first two are kind of just reinforcing each other, aren't they? This third point here is interesting. An object will remain stationary in a liquid it has equal density with. What that means, if we have a liquid and we put an object in there that has the same density, wherever we place it in the liquid, it will neither rise nor sink. It will stay exactly where we put it, which is kind of cool. So let's just have a quick look at calculating a density. It says, what is the density of oxygen gas if a 15-litre sample has a mass of 21.7 grams? So to calculate density, we take mass and we divide by volume. So they kind of give you a giveaway there. That's the mass, isn't it? 21.7 grams. And then that means, well, this must be the volume, which is consistent with the unit label of litres. So there it is, and we're going to get our answer in grams per litre. Both of these numbers have 3 significant figures. So whatever answer we get from the calculator, we're going to round off to 3 digits. So that gives us a density of 1.54 grams per litre. Okay, so that concludes our review of the International System of Units.